Physics aims to help us understand how the universe and everything in it works, from the largest things we know of, galaxies and galaxy clusters, all the way down to the smallest elementary particles that make up everything. So far, there's a lot of things scientists seem to have mostly figured out, such as gravity and quantum physics, and those seem to be the main things that we need to understand how everything works. Gravity makes that the Earth orbits nicely around the Sun, and you don't fall apart into a subatomic mess because of quantum interactions. Now, the two main theories that physicists have come up with over the course of a few centuries are general relativity, the scientific theory that describes gravity, and quantum physics, which describes the behavior of atoms and subatomic particles. The Standard Model describes these particles and the three kinds of interactions between them: electromagnetism and the strong and weak nuclear interactions. Now, while these theories work exceptionally well to explain most things that we can observe, as it is, the Standard Model seems to be incomplete and there are still major questions that remain, like dark matter, for instance. We can only observe the gravitational influence it has in the universe, but we don't know what it is exactly. We can measure galaxies are heavier than the amount of stuff we can see in them, so something must be there, but it doesn't emit, reflect, or absorb any kind of electromagnetic radiation. We can only detect the gravitational interaction. Maybe we'll find a particle we can add to the Standard Model, but you need to remember that dark matter, for now, is a placeholder term for this phenomenon that we can detect but not explain, at least not yet. And then there's also dark energy, which seems to be responsible for the accelerating rate at which the universe is expanding, but we also don't really have an explanation for that, only observations and hypotheses. Another one of the biggest remaining problems in physics today is the search for the so-called theory of everything, a theoretical framework of physics that fully explains and links together all aspects of the universe and would consequentially explain dark matter and dark energy. The main issue is that general relativity and quantum physics don't get along. But to be fair, they usually don't have to have anything to do with each other at all. If scientists want to explain and predict how planets, stars, galaxies, and clusters and superclusters interact with each other, they have general relativity for that. If they want to explain electromagnetism and the strong and weak interactions, they have quantum physics for that. But there are a few times and places that would require a unified theory of gravity and quantum physics to describe what happens there. Black holes and the beginning of all of space and time, the Big Bang. Now, I find one of the most important aspects of understanding science is understanding how we got to this point. So let's dive a bit into the history of how our current theories came to be. Wanting to find a way to explain existence goes back a long time. One can argue all the way back to the first humans. After all, existence is often strange and unpredictable. And as intelligent beings, we have found numerous ways to try and make sense of what happens all around us and inside us. Many ancient civilizations studied the night sky, the stars and the 7 planets visible to the naked eye, and so were able to predict their movements, including lunar and solar eclipses. Up until the 18th century, astrology, the idea that the apparent motion and positions of the stars and planets influenced life on Earth, was considered a valid science closely tied to astronomy, alchemy, medicine, and meteorology. The debate between the universe either having a beginning or eternal cycles can be traced all the way back to ancient Babylonia. In Hindu cosmology, time is infinite with a cyclical universe, where the current universe was preceded and will be followed by an infinite number of universes. Natural philosophy was the predecessor of modern science, and as the name suggests, it aimed to make sense of the universe by rational thought. To dumb it down a little bit, natural philosophy revolved around coming up with hypotheses, ideas on how everything works, by thinking about it really hard. The ancient Greek especially had many natural philosophers we still know about today, like Socrates and Plato, for instance, who thought long and hard about pretty much any field of science and knowledge relevant to their time. Some of their ideas turned out to be correct, but just as many other ones turned out to be pure fantasy. And whatever idea became dominant in society was more a matter of who was more popular and also whose work survived over time, because many books and writings by these ancient philosophers were sadly destroyed and lost forever. A famous example of an idea from natural philosophy that survived and was generally accepted in society for centuries is the idea that the Earth is the center of the universe. There were ancient natural philosophers that rejected this idea and said that the sun was at the center, but their ideas were just less popular and were forgotten. Until Galileo Galilei modified telescopes to study the sky with, and found evidence that suggested the Earth indeed revolved around the sun instead of the other way around. A famous example of an idea from ancient natural philosophy that turned out to be more or less true is the idea of atomism, which proposed that the physical universe is composed of fundamental, invisible, and indivisible components. The word atom comes from the ancient Greek word atomos and means uncuttable. The concept of atoms also appears in ancient Indian philosophy. And to be fair to the ancients, they did not have the means to study nature like we do. The first telescopes and microscopes were still centuries away from being invented, and so thinking hard about stuff was one of the only ways they really had to make sense of everything. And sure, they were very good at making observations and doing math. After all, the ancient Greek were the first to make a pretty accurate calculation of the circumference of the Earth by using 2 sticks and knowing geometry. So they were not dumb, they were just a product of their time, as we all are. Who knows what humanity will think of our society and science 5,000 years from now. Following atomistic thought, the mechanical philosophy of the 17th century posed that all forces could ultimately be reduced to contact forces between atoms, back then imagined as tiny solid particles. And this line of thinking compared the universe to a large-scale mechanism, like an extremely huge and complicated machine. But also in the 17th century, Isaac Newton published his book Mathematical Principles of Natural Philosophy, in which he achieved the first great unification in physics and established classical mechanics. Newton formulated the laws of motion and universal gravitation, and these formed the dominant scientific viewpoint for centuries to come, until Einstein and his theory of relativity came along. Newton based his formulations on Galileo's work on terrestrial gravity, Kepler's laws of planetary motion, and the phenomenon of tides. He explained these apparent actions as a distance under his one single law of universal gravitation. Unlike in mechanical philosophy, Newton's work suggested that not all forces in nature are the result of things coming into contact. As we know today, gravity only really becomes relevant between things that are large enough. The moon does cause the tides because of its gravitational influence, and the sun helps too. But the atoms and molecules that make up the water in the ocean stick together because of quantum interactions. In 1814, the French scientist and philosopher Pierre-Simon Laplace famously suggested that a sufficiently powerful intellect could, if it knew the position and velocity of every particle at any given time, along with the laws of nature, calculate the position of any particle at any other time. With this, he envisioned a combination of gravity and mechanics as a kind of theory of everything. But I have to add that our modern understanding of quantum physics implies that uncertainty is inescapable, so his idea could probably never happen. Even if you ignore quantum mechanics, chaos theory suggests that any sufficiently complicated system is unpredictable by default. There's just too many variables and possibilities. In 1820, Danish physicist and chemist Hans Christian Ørsted discovered a connection between electricity and magnetism. He found that a compass needle was deflected from magnetic north by a nearby electrical current, and this confirmed a direct relationship between these phenomena. This was quite groundbreaking because for a long time magnetism and electricity were considered separate things. Ørsted's experiment triggered decades of scientific work that culminated in Scottish physicist James Clerk Maxwell's theory of electromagnetism in 1865, in his paper A Dynamical Theory of the Electromagnetic Field. It was the first theory to describe electricity, magnetism, and light as different manifestations of the same phenomenon, electromagnetism, and a second great unification in physics. Maxwell's theory led him to predict the existence of radio waves, and his discoveries helped usher in the modern era of physics, laying the foundation for quantum mechanics and special relativity. Many scientists consider him one of the greatest physicists to have ever lived, just behind Isaac Newton and Albert Einstein. Einstein himself, when he visited the University of Cambridge in 1922, was told by his host that he had done great things because he stood on Newton's shoulders, but Einstein replied, "No, I don't. I stand on the shoulders of Maxwell." Another prominent scientist of the 19th century was Michael Faraday, best known for establishing the concept of the electromagnetic field in physics and a ton of practical research into electricity and magnetism. It was largely due to his efforts that electricity became practical for use in modern technology. He was a self-taught scientist and experimentalist, and in fact he didn't know complicated math other than basic algebra. But his work influenced Maxwell's theory, and another reason I mention him here is that he was the first person to attempt to find a connection between electricity, magnetism, and gravity. Kind of like a theory of everything. But he never succeeded. Another huge development in the 19th century was evidence for the existence of atoms, so the ancient Greek idea proved to be true in the end. British chemist John Dalton noticed that in chemical compounds, the separate chemicals always came in whole numbers. He suggested that the reason for the whole numbers of chemical compounds was because of atoms, the smallest particles possible, and so you simply can't have half an atom or 0.2 of an atom. Dalton then formulated his atomic theory, with the main points being: elements are made up of extremely small particles called atoms. Atoms of a given element are all identical. Atoms cannot be subdivided, created, or destroyed. Atoms of different elements combine in simple whole number ratios to form chemical compounds. In chemical reactions, atoms are combined, separated, or rearranged. He was actually mostly correct, but in the meantime, scientists have discovered that atoms do consist of even smaller components: protons, neutrons, and electrons. And protons and neutrons consist of quarks, but that's for later. Another major event in the realm of electromagnetism right on the cusp of the 20th century was the discovery of the electron. Scientists had already observed this eerie glow inside a vacuum glass tube equipped with 2 electrodes with voltage applied. These were called cathode rays, and nowadays we know the negatively charged electrons coming from one end of the electrode are getting attracted to the positive charge of the other electrode. And when these electrons bounce off of the glass tube, they ionize the atoms of the tube, and this causes the glow. Cathode rays themselves are in fact invisible. In 1897, English physicist J.J. Thomson showed that these rays were composed of previously unknown negatively charged particles, and he calculated they had to be much smaller than atoms. Atomic theory and electromagnetism research were 2 major puzzle pieces that would lead to quantum theory in the early 1900s. German physicist Max Planck is considered the father of quantum mechanics. The true nature of light was a thing scientists were still struggling to fully explain using classical physics. Some things were just not adding up, theories were incomplete, and the question whether light was a wave or a particle remained unanswered. Planck had the idea to assume light was emitted and absorbed in tiny packets of energy, which he dubbed quanta, after the Latin word for how much, where we also get the words quality and, well, quantity from. For Planck, the quantization of light was a kind of mathematical trick to solve an equation, and not really meant as an accurate depiction of reality. But Albert Einstein and other contemporary physicists like Niels Bohr, Louis de Broglie, Max Born, Paul Dirac, Werner Heisenberg, Wolfgang Pauli, Erwin Schrödinger, and others realized there was a deeper truth to Planck's little quantum trick. And it would revolutionize physics. We have Einstein to thank for 2 of the most groundbreaking theories in modern physics. Special relativity tells us that, first of all, the laws of physics are the same in all frames of reference, and secondly, the speed of light in a vacuum is the same for all observers. The theory of general relativity provides a description of gravity as a geometric property of space and time, or 4-dimensional spacetime. Mass affects spacetime, curving and warping it, and this affects all things existing in spacetime, be it matter or radiation. Newton's old law of gravitation worked great for most things, but Einstein's general relativity was able to explain things that Newton's laws could not. The planet Mercury, for instance, makes an orbit around the Sun just a little faster than Newton's law predicts, and this is because the Sun is massive enough that it bends spacetime in such a way that it affects the orbit of Mercury in a way we can measure. General relativity also predicted things like gravitational waves, gravitational lensing, and gravitational time dilation. And that last one matters more than you might expect. Clocks effectively run slower when they're closer to a massive object. And this is something engineers have to take into account when they're building satellites, for instance. Because satellites orbit quite far from Earth's surface, their clocks need to be adjusted for this, because they run slightly faster than they would on Earth, and this is important for precise communication and GPS systems. If engineers ignore general relativity, GPS wouldn't work well because the clock in the satellite would run ahead and give wrong information about your position on Earth. General relativity may seem like a lofty and difficult theory for only the smartest scientists, but it does affect our daily lives in a significant way. Einstein would spend a good chunk of his life trying to find out how electromagnetism and gravity were manifestations of one grand underlying principle, his so-called unified field theory, but he never succeeded to find this kind of theory of everything. Contemporary physicists Oscar Klein and Theodore Kaluza also attempted to formulate a unified field theory, and they tried to make this work by adding a fifth dimension on top of the 4 spatial dimensions plus time. This fifth dimension had to be extremely tiny and kind of curled up in a loop, and so the Kaluza-Klein theory was a sort of predecessor of string theory, which we'll talk more about later. It was in fact this theory that Einstein wanted to develop further into something that could explain all the fundamental interactions and particles known back then. But most physicists at the time were much more focused on the emerging framework of quantum physics, and Einstein never fully accepted it anyway. In the mid-1920s, quantum mechanics was developed to become the standard formulation for atomic physics. In 1923, the French physicist Louis de Broglie put forward his theory of matter waves by stating that particles can exhibit wave characteristics and vice versa, and so the concept of wave-particle duality was born. Building on de Broglie's approach, modern quantum mechanics was born in 1925, when German physicists Werner Heisenberg, Max Born, and Pascal Jordan developed matrix mechanics, the first autonomous and logically consistent formulation of quantum mechanics, which was a pretty huge deal because at this time matrices were considered to belong to the realm of pure mathematics and didn't have much of a place in physics. Well, not anymore. Also in 1925, Austrian physicist Erwin Schrödinger invented wave mechanics, providing scientists with another way to help them predict quantum mechanical systems, much like how Newton's second law helps us predict the behavior and evolution of a physical system in classical mechanics. If you want to remember Schrödinger for something other than his thought experiment with the cat in the box, remember him for this famous equation. The 1920s also saw some groundbreaking new science when the proton and the neutron were discovered to be particles that make up atomic nuclei. If you're wondering how scientists were able to prove the existence of particles that no one at the time was able to see, they did clever and complicated experiments with chemistry and magnets and electricity, and their conclusions either predicted or confirmed the existence of particles that atoms are made up of. And all of this was useful for the emerging field of quantum mechanics. It was not just complicated math, experiments showed that it all made perfect sense. As fascinating as this all is, I'm not gonna dive much deeper into it because this video is gonna be many hours long otherwise, so maybe some other time. And I know quantum physics seems very complicated because it's so counterintuitive, especially compared to classical mechanics, which is very intuitive because we're confronted with them on a daily basis. If you push a ball, it's not going to suddenly roll backwards. I suppose a good analogy would be, imagine you played checkers your whole life. And then someday someone gives you a chess set, and now you have to learn a whole bunch of new rules to play this game, but once you understand the rules, it does make sense and you can make logical predictions. The rest of the 20th and 21st centuries saw amazing discoveries about the fundamental rules of existence and the formation of the standard model as it exists today. It was developed in stages throughout the latter half of the 20th century through the work of many scientists worldwide, with the main formulation being finalized in the 1970s, when the existence of quarks was confirmed. Quarks are the elementary particles that make up protons and neutrons. They come in 6 flavors: up, down, strange, charm, top, and bottom. Up and down quarks are the least massive and therefore most common flavors of quarks that exist. The heavier quarks can only form in high-energy collisions like with cosmic rays or in particle accelerators, and they quickly degrade into lighter ones. The quarks that make up protons and neutrons are held together by the strong nuclear interaction, and the particle responsible for mediating this interaction is called the gluon. The strong interaction was hypothesized already in the 1960s, since scientists couldn't explain what held the protons and neutrons in the atomic nucleus together. The positively charged protons should repel each other and cause the nucleus to fall apart, but since things exist and the universe isn't filled with just loose particles bouncing off of each other, there had to be something else going on, and so the strong interaction was discovered. The weak interaction is responsible for radioactive decay, specifically beta decay, and while radioactivity was discovered in 1896, the underlying mechanisms weren't fully understood until the weak interaction was discovered. The particles that mediate the weak interaction are the W and Z bosons, and these weren't directly confirmed until 1983. Now, the electron was already discovered back in 1897, but since then, different flavors of electron-like particles have been found, and this family of elementary particles are called leptons. We also have the muon, the tau lepton, and 3 flavors of neutrinos. Neutrinos are kind of weird particles. They interact via the weak interaction and gravity, I suppose, but because the weak interaction has an extremely short range and the mass of the neutrinos is so small it was long believed they had no mass, they interact very little with anything, so it's very hard to detect them at all. So yeah, they just sort of exist and that's all we know. They just fly through most things all the time. While Max Planck was the first to quantize light, the word photon wouldn't be coined until 1926, but now we know this particle is the one mediating the electromagnetic interaction and the weak interaction. In the 1950s and 60s, evidence was found that these two interactions are aspects of the same thing, even though they seem very different at everyday low energies. At high enough temperatures, these two interactions become the electro-weak interaction. But we're talking extremely high temperatures, like 10 to the power of 15 degrees Kelvin. And scientists suspect this kind of temperature has not occurred much at all since the quark epoch, a moment very shortly after the Big Bang itself, when the universe was still hot enough that quarks could not bind to each other to form composite particles like protons and neutrons. So it was even too hot for the strong interaction to do anything. Now, if you're wondering how scientists know all of this, it's because they did a lot of complicated math and simulations and smashed particles together inside particle accelerators. And this is the result. And I know technically nobody can know 100% for sure what the Big Bang was like, because you can't go back and observe it. So the second best way we have to have an idea of what that moment was like is doing math. Also, the highest human-made temperature ever achieved on Earth was about 10 to the power of 12 degrees Kelvin, but only for fractions of a fraction of a second inside the Large Hadron Collider. Okay, we're almost done with all these particles and interactions, and then we can finally start to talk a bit about candidates for a theory of everything. Last but not least is the Higgs boson. And this is one many people have heard of because it was proven to exist back in 2012. Even though it was already predicted all the way back in 1964 by Peter Higgs and a team of 5 other scientists when they proposed what is now known as the Higgs mechanism. A way for some particles to acquire mass, these so-called gauge bosons, gluons and the W and Z bosons. Without the Higgs mechanism, these would be massless. But they do have mass, and so something had to be responsible for this, and so the Higgs boson was proposed and later proven to exist. So just to go back to my checkers and chess analogy, not only did we discover we're not playing checkers at all, but rather a completely different game, and we have to figure out all the rules all by ourselves, and we also have to find how many pieces there are for the game and what they do in the game. Isn't quantum physics fun? Anyway, back for the search to what some call the holy grail of modern physics, finding a unified theory that describes all particles and interactions. Like I said, gravity and quantum mechanics don't get along. On the large cosmic scales, general relativity matches observations, but quantum principles don't seem to apply. The same happens when you try to look for the principles of gravity in the subatomic world. Gravity is actually so weak it can't be detected or observed on the scale of particles, where everything is governed by electromagnetism and the weak and strong interactions. Physicists have been trying to find a way to make this all work for a long time, as we've seen, but so far nobody has found a way, and some scientists even argue that an overarching theory might not be possible in the first place. Probably the most famous attempt at a unifying theory is string theory. I've mentioned Kaluza and Klein before and their idea to add a tiny curled up fifth dimension to the four we're familiar with. Scientists have also tried to quantize gravity with particles called gravitons to govern this interaction, and on the surface that seems to make a lot of sense, but when they tried to make a full theory with gravitons they ran into trouble. Answers that were supposed to be finite turned out to be infinite, and so basically you can't use them to predict anything. What string theory does is replace all particles with extremely tiny vibrating strings that twist and turn in complicated ways that, from our perspective, look like particles. It's kind of like how power lines look one-dimensional from a bird's eye perspective, but to a tiny ant crawling on the line, it's a three-dimensional surface. Strings with a certain length and kind of vibration would look like electrons to us, others would look like quarks, and so on and so forth. String theories seemed very promising at first, but since the 1960s, it has grown to be a lot more complicated than anybody had anticipated. It needed a total of 10 or even 11 dimensions to work, so with 6 or 7 dimensions curled up invisibly. And so far, there's no evidence for any of this. Another problem is that the way that a string vibrates depends on how it's wrapped up. When mathematicians tried to calculate the number of possibilities of this wrapping up, they arrived at astounding values. The number often quoted is 10 to the power of 500. A 10 with 500 zeros after it. Each of these wrapping combinations represents a possible universe in 4 dimensions, but only one of them would represent our universe, with the laws of physics that we study. 1 out of 10 to the power of 500. How do we pick the right one? Is there even a right one, out of what seems to be billions upon billions of different possibilities? String theory does give some sort of scientific legitimacy to the concept of the multiverse, where alternate universes exist alongside ours, and where the laws of physics may be completely different. Now, while you can make this work mathematically, there's no evidence for a multiverse existing at all. Sorry. Now let's go back a bit to the idea of trying to quantize gravity. Loop quantum gravity is an active field of research in physics still, and it approaches a unified theory of physics from Einstein's theory of general relativity. Instead of trying to match gravity with quantum physics, it assumes the physics we observe arise from space-time itself. Quantum physics and string theory work off of the idea that space-time is the background in which all things that exist and interact takes place. This background can warp and bend and affect the paths of particles, but that's about it. All physics happens on top of that background spacetime. In general relativity, however, spacetime is the main character, not the background, and the warping of spacetime gives rise to the physics of gravity. And so maybe gravity is the mechanism of spacetime, and so if we want to formulate a theory of quantum gravity, uniting all the interactions we can observe, we ought to try and seek a quantum theory of spacetime. And so we'll automatically end up with a theory of quantum gravity. What loop quantum gravity tries to do is quantize spacetime itself. This means that there could be a fundamental unit, a discrete chunk of spacetime, but on such a small scale that we can't perceive it. If you zoom all the way in on a picture, you'll start to see the pixels or dots it's made up of. Maybe if we somehow found a way to zoom in on spacetime itself, we would see the chunks it's made up of. Time wouldn't be smooth, so to speak, it would continue into the future in tiny clicks. Motion wouldn't be fluent, it would just be extremely small steps, kind of like how a movie or video game needs at least 24 frames per second to look fluid, but it is made up of separate images. This seems very logical and promising, but you may have guessed loop quantum gravity comes with its own problems, otherwise it would just be the accepted grand unified theory of physics by now. One problem is that loop quantum gravity needs to contain within itself general relativity. If your math for this idea works on the very smallest scales, it should work on scales at which general relativity and Newton's old-fashioned laws are relevant. But so far, nobody's figured out how to make that work. Another issue is that loop quantum gravity as a theory has failed to produce any of the predictions we can already make with either general relativity or with the standard model. And you should know that this is actually a problem with all attempts that have been made at quantizing gravity. So I guess this whole video is just a pretty long-winded way of telling you, no, we're not quite there yet. We're probably still pretty far away from a theory of everything. Now, like I mentioned before, dark matter and dark energy are still two huge mysteries in physics neither general relativity or quantum physics have an answer for. So it would seem that if or when, hopefully when, we can solve these, we'll be a few steps closer to a unifying theory of some sort. In the case of dark matter, we can observe gravitational effects that have no other explanation. It's not dark gas or any sort of ordinary matter that's hard to detect. We can only detect dark matter because it has a gravitational influence, but it doesn't seem to interact with anything in any other way. The most prevalent idea is that there could be some kind of undetected subatomic particle involved. Another idea is that dark matter is mostly made up of primordial black holes that formed during the early epochs of the universe, before any stars existed. Some physicists even believe that the theory of general relativity itself needs to be modified. But so far, none of the proposed modified gravity hypotheses can describe every piece of observational evidence at the same time. And this suggests that even if gravity has to be modified, some sort of dark matter will still be needed. Dark energy is arguably even stranger. Observations of the redshift of supernovae and large structures such as galaxies and galaxy clusters show us that the universe is expanding at an accelerating rate. But since scientists have no idea what could cause this, they simply dubbed it dark energy. One idea that seems likely is that it's an intrinsic fundamental energy of space itself that may be constant or fluctuate over time. Another is it could be some kind of undiscovered force or interaction. Or maybe it's tachyons, hypothetical particles that travel faster than light and so backwards in time. Now that hypothesis is a bit out there, to be fair. Either way, a lot more research needs to be done and a lot more data needs to be gathered, but this is in fact hard because both dark matter and dark energy are so elusive and difficult to study. A unified theory probably won't happen before we solve these problems. And then there are in fact some arguments against a theory of everything. Well, not so much against the idea, but that the search for it might be fruitless and it could just never happen. Gödel's incompleteness theorems were published by Austrian mathematician Kurt Gödels in 1931. In the realm of pure math, they mean that every mathematical system will have some statements that can never be proven. That there are true statements about numbers that can be proven by mathematical facts or axioms. Gödels proved that any set of axioms you could posit as a possible foundation for math will inevitably be incomplete. Proving in math is something for the nerdiest nerds. It's the purest kind of math you can be doing, so I'm not going to dive too deep into it. But basically, what this can mean for a physical theory of everything is that you could possibly never come by a complete set of mathematical truths for how existence works. Another thing to consider is that there currently is no physical theory that is believed to be precisely accurate. We can view the history of physics as a series of successive approximations that allowed us to make more and more accurate predictions of wider and wider range of phenomena. Obviously, we cannot honestly say a physical theory is 100% accurate, and achieving that might not be possible. That doesn't mean scientists are wrong about everything, it's just the nature of doing physics and trying to describe and predict reality. I mean, this whole video is about how scientists as of yet haven't succeeded in coming up with a theory that can describe and predict everything we can observe. But we seem to have come a pretty long way either way. In the end, science is a process we use to try and find out how everything works as best as we can. Always keeping in mind we're flawed beings and we make mistakes all the time, and no scientist worth their salt is going around saying science can never be wrong. In fact, it's more fun to be wrong because that means scientists can do more science. It's quite literally what they live for. The scientific method is the best way we've come up with to try and understand the universe we find ourselves in. And that means we constantly readjust our view when we find new evidence that suggests something different than we previously assumed, or expand on our old ideas. Newton's laws of gravitation were great, but they turned out to be incomplete. Einstein shed new light on our understanding of physics, and while general relativity is one of the most solid theories we currently have that has withstood many tests for the past century or so, it might someday turn out to be incomplete as well. And maybe someday we'll find out whether a so-called theory of everything is possible. Or maybe not. Only time will tell. Thank you for watching. I hope you learned something new today, and I will see you in the next video.